So the presentation today is going to focus on methods that we can use to minimize differences between groups in a quasi-experimental design. But before we get started, I thought I can introduce myself a little and then let my co-presenter Chris introduce himself. So my name is Parsad. I'm a senior scientist in the Social and Economic Policy Division. I work on the technical assistance team for the first in the world evaluation, as I mentioned earlier. I also do technical reviews for the I3 contract as well as Works Clearinghouse. And I also do technical assistance for the DOL contracts that we have. Chris?
And I'm Chris Price. I'm also a technical assistance provider on this first in the world contract, and I've also done similar kinds of technical assistance on other evaluation technical assistance contracts, including the I3 grant program and the Striving Readers grant programs.
Okay, so let's get started. So what do I hope that you take away from this webinar at the end of the session? Our focus today is how to achieve equivalent treatment and comparison groups in quasi-experimental studies and to help us to meet evidence standards. And in order to do so, we are going to provide guidance on a couple of topics. The first is how to select characteristics to match on and what types of characteristics might be important to match on when you're trying to establish your equivalent groups. To provide guidance on methods you can use for matching and also help you to understand how matching can help you to meet what Works Clearinghouse evidence standards. So why is it even important that we have equivalent groups? The goal of any rigorous study would be to produce the best evidence of effectiveness that we can produce. And ideally, we'd probably want to use a randomized controlled trial to do so. However, and in some cases, it's not always feasible to do randomized control studies. And so what we ideally want to do is basically measure the outcome that the group that received the intervention received, and we also want to compare that outcome to what would have happened to the same group without the intervention. Because the group's treated, we really cannot observe that outcome, so we have to estimate it. And in order to do that, we want to group as similar as possible to the treatment group so that we can make that estimate that outcome. And we want to make sure that when we observe a difference between these two groups, that it's because of the intervention, not because of some pre-existing difference between these two groups. So that's why it's important that we have equivalent groups. Before I get started, I want to set the stage a little and give you some details of the matching methods. So to begin with, imagine you have a treatment group, and where do you even begin to look for a comparison group? And one of the places you can look for clues and where to start to look is basically looking at your eligibility criteria for the treatment group. So if we can clearly define the eligibility criteria for the treatment group, then you can start looking to construct your comparison samples. So for example, if your treatment targets 4-year institutions, you probably want your comparison group to also include 4-year institutions and not 2-year colleges. Likewise, if your intervention targets students who are freshmen and they're first-generation college goers who are eligible for Pell Grants, you probably want similar types of students in your treatment group as well. So where to start forming that comparison group, look to your eligibility criteria for some clues. The other thing I want to say about the matching process and making these groups equivalent is very much an iterative process, in the sense that we probably choose your matching method that you want to use to create the equivalent groups. We'd probably implement that approach. Then we want to check for the equivalence of groups on the key baseline variables or the variables you use to match on. If you're satisfied with the equivalence, then you're done and you can stop. But if you're not, then you probably want to start to do some sort of tweaking, either change your matching method, change the variables you're matching on, or tweak something or the other, but you'll keep going until you're satisfied with the equivalence that is between the treatment and the comparison group. So what are we going to cover today? I think the first thing we're going to discuss is basically how to select those variables to match on, what's important to match on. The second topic would be, now that you've got your variables, how do we decide that a treatment unit is close or similar to a comparison unit? And so we'll discuss distance metrics that you can use to assess those differences. The third topic that we will discuss is the methods that you can actually use to do the matching once you've identified your characteristics and the distance measure you want to use. And once you've got a match, then I'll touch briefly on how to assess baseline equivalence and how to handle the matching in the analysis. There is some terminology I would like to go over with you that you'll hear come up throughout the presentation, and the first is distance, and I think I've alluded to this before. The distance is basically a measure of similarity between your treatment unit and your comparison unit. The smaller the distance, the more similar the units are. The larger the distance, the less similar they are. You'll also probably hear me talk about confounders, and when you think about a confounder, you want to think about a variable or a characteristic that's related to both the outcome and selection into the treatment. For example, you can think of things like motivation. If I say T's throughout this presentation, I mean treatment group units. If I say C's, I mean control group units. So let's start with how do we go about selecting or matching variables. This is probably the most important thing you'll do through this whole process, is identify which variables you want to match on. And the goal is to minimize or control for the effects of those confounders, so that when we form the group, they're as similar as possible on those confounders. When we think of selecting variables, we want you to include as many variables as you can, given sample size, as many measures as possible that are related to the outcomes. And when you think about these outcomes, you want to think about baseline measures of the outcome or a close proxy in the same domain. In the post-secondary Works Clearinghouse protocol, some other outcomes that you could think about is an achievement score or a socioeconomic status indicator for students. And we also want you to think about variables that's strongly related to selection into the treatment and the outcome. And as I mentioned earlier, those are confounders, so you want to think about things like motivation and interest. Other examples could be your class or your major or the number of entering credits that you might have. So those are variables we want you to think about. Most importantly, we want you to ensure that these variables are measured at baseline, because we don't want these variables being affected by selection into the treatment or the comparison group. So that's one of the other key characteristics of these measures that you're looking for. I also want you to think that if you find a variable that's related to the selection into treatment but not the outcome, shy away from using those variables, because they could increase bias in your estimates. If we have a large number of variables and you have to figure out which ones to include or not, think about the variables that are related to the outcomes. Those are the priority variables. So I wanted to give you some examples of different types of variables you can include when you're matching on. And then when you think of variables, you might want to think about, do you want an exact match on these variables? Is a close match good enough? Are all the variables important to be matched on? Or are there some variables that you can match on very close, but you have loose matching on other variables? So before you think about a variable, think about those questions as you're trying to select these variables. If you're matching on student characteristics, some of the things you might want exact matches on are things like time of enrollment, intended degree program or major, and think about your eligibility criteria in there as well. Things that you might want to get close to but not exact matches on are things like your pre-intervention measures of the outcomes, baseline academic achievement, socioeconomic status indicators. So those are some student characteristics that you could think about. If we are matching at the using institutional characteristics, you might want to get exact matches on institution type, the 2-year versus 4-year institution. You might want to get exact matches on location and the degree programs offered. But then you might also want matches that are not exact but close on things like average SAT or ACT scores of your entering students, selectivity of the institution, and graduation rates of the institution. So those are examples of variables that we can use to match on. One of the questions that I'm often asked is, what happens if I omit an important variable from my matching? Or what if I cannot observe one of these variables that I know is important? Because you're probably not going to be able to measure everything that you think is important. And unfortunately, if we do that, it can lead to biased impact estimates. And we can think about this using an example. Suppose we have 2 groups that we've matched, a comparison intervention group. And we have observed characteristics on achievement and demographics, and we've matched these groups and their equivalent on those variables. But suppose we know that motivation is really important, but we cannot measure that. And so you can think that your intervention group is more motivated if you smile on their face, and look at the comparison group, they're probably less motivated. So when we see outcomes and we observe differences in those outcomes, is it because of the intervention that they just were exposed to, or is it because that one group is more motivated than the other group? So that's the types of things that can lead to biased impact. So what can you do? I don't know that there's much that we can do, but because of this reason, because there's a possibility that there's some unobserved variable that we cannot match on, it's one of the reasons that the highest evidence rating that the WWC assigns to acuity is meet standards with reservations. So the takeaway lesson, or the lesson that I want you to take away from this, is match on as many confounders as we possibly can. Keeping in mind, for post-secondary studies, you really want a proxy of that baseline measure to be equivalent on that, or an SES indicator and achievement score. So now that we've talked about sort of identifying these characteristics or these variables that we can match on, and we have them, how do we use them to decide whether or not a comparison unit is close or similar to a treatment unit? And there are distance metrics that we can use to accomplish this, and the goal of these metrics, or what you want to do, is minimize the differences between the groups. So you can think about if you had just one variable that you were matching on. So let's say, for example, age. It might be very, very easy to just match age, looking at matching all 15 to 16-year-olds or all students that are less than 12 or something like that. But as you add more and more variables to be matched on, then you can't quite do the matching using eyeball or some similarity, looking at the groups or something like that. So you need these metrics to help. And the different metrics that you can use are propensity scoring, Mahalanobis distance, scaled Euclidean distance, and eyeball similarity, which is exactly what it sounds like, just using your eyes to figure it out. So I'll describe each of these metrics in turn. And the first is propensity score matching. But before we even talk about this metric, I want to give you some intuition of what a propensity score is. So a propensity score, or the propensity, is basically a model estimated probability of being treated. That is, what is the probability of you being a treatment group given what we know about you and using these covariates that we have measured. You can think of a model where the dependent variable is basically the treatment group indicator, and your independent variables are those baseline or matching variables that we want to use. Most common, people use a logit model, but you can also use a probit or a linear model to estimate these propensities, which probabilities. Once you've got the probability is estimated, how the propensity score matching work is basically you look at the treatment and comparison unit propensity scores, and if propensities are similar, then they're very close. So that's how the propensity score distance metric works. Propensity scores, basically you'd want to use this metric if you have large sample sizes or you have lots of matching variables, and each of those matching variables are of equal importance, like there's no variable you want to match more on than others. You can definitely estimate these propensity scores using standard software and SAS, and STATA has capabilities of doing this. It might not be the right choice if you have very few matching variables or small samples, or if some matching variables matter more than others. If you want closer matches in some or looser matches in others, this might not be the best distance metric to use. The Mahalanobis distance and the scaled Euclidean distance is very similar in the sense that basically they identify all the potential treatment comparison pairs, and then it creates samples with all these possible combinations, and it selects the sample that has the smallest average square distance. So this is how the Mahalanobis distance and scaled Euclidean distance works. In terms of the pros and cons of each, the Mahalanobis matching works well with smaller sample sizes, if you have few matching variables, and if all the matching variables are of equal importance. SAS and STATA don't have this capability in its core units, but they are user-written macros and packages you can use to figure this out. It's not the right choice if you have large samples and lots of matching variables, and in cases where you want to match more closely or exactly in some variables but not others. For the scaled Euclidean distance, this works well with smaller sample sizes if you have fewer matching variables. And unlike the case with the Mahalanobis distance, if you have some variables that you want to prioritize matching on over others, this would probably be the metric you would use. It's not the right, probably not the right choice if you have large sample sizes, if you have many matching variables, or if all the matching variables are of equal importance. And this metric do require specialized software. So eyeball similarity is something, it's exactly what it sounds like. It's using your eyes to figure out how close matches are. It works if you have a very small potential pool of comparison units. And basically what you want to do is simply just choose the set of comparison units that is most similar to the treatment units on your matching characteristics. So if you think of an example, suppose we have 2 treatment schools within a district and you want to identify 4 comparison schools within the same districts, you might be able to go out and figure out which 4 schools are best matched based on demographics and achievement scores. This method would work well if you have small sample sizes, you have very few matching variables, and you have some priority on how you want to match these variables. No specialized software is required other than your eyes and some maybe Excel sheets. It's definitely probably not the right choice if you have large sample sizes and lots of variables, or all the variables are of equal importance on matching. So we've identified our variables. We've talked about how we're going to figure out whether or not a treatment unit is close to a comparison unit. So how do we actually go about matching these units? There are several methods we can use. There's one-to-one, one-to-many, many-to-many, and we'll discuss these in turn in the next few slides. So how does one-to-one matching work? Basically, we identify for each treatment unit a comparison unit, one comparison unit we match to each treatment unit, and you identify the comparison unit with the smallest distance, basically. This is a really good option if you have nearly equal number of potential comparison units, as well as if you have a limited budget and collecting your outcomes for those comparison units are expensive. You probably don't want to use multiple comparison units for each treatment unit. One of the drawbacks of this method is that it might have a smaller sample size, so it might have lower power relative to 1 to k matching. So for 1 to k matching, how this algorithm works basically is for each treatment unit, you select a comparison unit with the smallest distance, and you do that for each treatment unit. And then you have a second pass, and you identify for each treatment unit another comparison unit. And you keep doing that how many times you want to do that, basically. So you're identifying several comparison units for each treatment unit. One of the cautions with this algorithm is as you go along, you need to monitor those distances between your treatment unit and your comparison unit. And the reason for this, you can imagine, like, the more comparison units you try to find for each treatment unit, those distances might be getting, larger and larger, and so they might turn out to not be very good matches. And so you want to monitor that, and if the distance grows, you might want to stop it. You might even want to go, you know what, I need to go back a few steps and just keep the first 2 matches or the first 3 matches. But it's very important to just keep an eye on how those distances are growing as you identify units. Okay, so this is a good option if you have a very large pool of potential comparisons. It also improves power relative to the 1-to-1 matching because you might have larger sample sizes, but those power gains diminishes once you start to identify 4 or 5 comparison units for each treatment unit. It's not a good option if you have equal or fewer number of potential comparison units than treatment units. The next type of matching you can do is many-to-many matching, or sometimes it's referred to as stratification. And how this algorithm works, remember way back when we talked about this distance metric as a propensity score. So we basically have estimated those propensity scores for both the treatment and comparison units. You use those scores and you try to create like 5 or 6 strata, where within each of the strata, the comparison and treatment units have very similar propensity scores. Something that I want to say or caution you about is that because these propensity scores are the probability of being treated, you might have some treatment units that have such high propensities of being treated that you don't have similar comparison units, and you would probably have to discard those treatment units from the study. Likewise, on the other end, you might have some control units that have such a low probability of being treated that they have no similar treatment units, so you might have to drop those comparison units. And in the past, when I've done this, I've had people go say to me, like, is that bad that you dropped some of your treatment units from this method? And in all honesty, it's a trade-off between sort of internal validity and external validity. Internal validity, you want to establish baseline equivalence. You want these things to be as close as possible. In doing so, you have to discard those treatment units. Because you've done that, now you might not be able to generalize to all the treatment students, and so that's where your external validity suffers. But WWC really cares about external validity, so keep, internal validity, so keep that in mind. Once you've got your groups or your strata where you have similar propensities, when you're doing your impact models, if you're looking at baseline equivalence, everything has to be done within strata, and then you aggregate across strata to get an overall estimate. So what's the pros and cons to many-to-many matching? One of my favorite is that it's probably one of the methods that retains the largest sample size. You do not need specialized software to do this. You can do it in Stata or SAS. There is guidance available in the WWC on analyses using propensity scores that you can refer to for additional information. Propensity scores, however, does not ensure balance on the key baseline variables, and you probably have to tweak it multiple times to accomplish that. But again, one of the things I wanted to point out is that in the post-secondary protocol for WWC, the things that you really have to establish baseline equivalence on is that pretest measure of the outcome or a proxy, and if that's not available, you either one bounds on SES indicator and an achievement score, pretest achievement score. Another method that you can use for matching is weighting, and it's very similar to many-to-many matching. And how weighting works basically is that you look at comparison units, and then you reduce the weights of comparison units that are least similar to treatment cases. Likewise, if there are treatment cases that does not have any similar comparison units, you reduce their weights as well. One of the most common ways that people use is the inverse propensity score. One thing that you have to keep in mind if you use weighting is that you have to use these weights in all of your analyses. Be it impact, baseline, whatever you're doing, you have to use the weights, and you have to use software that basically correctly reflects the variance inflation caused by the variation in the weights that you can get. The pros and cons, like many-to-many matching, it can retain large sample size. Again, you do not need specialized software for this. You can do it in SAS or Stata. There is guidance available. And like I said before, it does not guarantee or ensure balance on the key baseline variables, so think carefully about the ones you really do need to establish equivalence on. And if propensity scores are very close to 0 or close to 1, you can have a huge sampling variance because of that variation. So you want to keep that in mind. So we've talked about the distance metrics we can use and how we can, what methods we can use to match treatment and comparison units. Another question you have to consider is whether or not a comparison unit can only be used once. So can it be used just to, once you've used it, you basically discard and cannot use it to match to another treatment unit? Or can a comparison unit be used more than once in several pairs? And so this first thing is matching without replacement. And so how this works basically is once a comparison unit has been identified as a match for a treatment unit, it's removed from the pool and cannot be used again to form another match pair. And this is really easy to implement. It's easy to analyze data if you've used without replacement matching. And there's no cons that I could really think of. If there's one someone knows, you can let me, but I cannot think of any. The next consideration, if you want to use a comparison unit more than once, this is called matching with replacement. And basically how it works is that if a comparison unit is paired with a treatment unit, it stays in the pool and can be used again to be matched to another treatment unit. If you have few available comparison units, this may be your only option. Like you might have to match with replacement. The con of this is very difficult to account for with replacement sampling analysis, but it can be done. It's just a little more tricky. So now that you know how to identify those characteristics and how to match and what you're going to use to match on, how do you decide which comparison unit is the best match for your treatment unit? And there are two methods that we can use to figure this out. The first is greedy matching with replacement. And basically how this algorithm works is that you start by arranging your treatment units in some order. And then the algorithm basically looks through your pool of comparison units. It identifies the closest or the nearest neighbor for that treatment unit, makes that match, removes that comparison from the pool. Then it goes to the second treatment unit on a list, goes through the same thing, finds the comparison units that's remaining in the pool with the closest match, make that match, remove the comparison from the pool, go to the third, and so on. So this method is really easy to program. However, if you just think about how I just described that method, it starts from the top of your sorted list and goes through finding the best comparison for each of those units. But it's very possible that the comparison unit that you selected for a treatment unit that's earlier in that list could have very well been a better match for a treatment unit that's lower down in that list. So the matching and the closeness that you get really is dependent on the order that we sorted that treatment list on. So if you don't want your matching affected by order, another method we can consider is optimal matching without replacement. And basically how this algorithm works is it finds all these matched pairs and creates these different samples, and it chooses the sample that has the smallest absolute distance across matched pairs. And so it's basically trying to find your best matches across all possible combinations. That's basically how your optimal matching is working. You might ask, suppose, two treatment units one comparison unit can serve as the best match for two treatment units. How do you figure out which one to make the pair with? And what this algorithm would do is basically select as the match a treatment case that has the worst backup match. So the pros and cons of optimal matching: it's not sensitive to order of the treatment units, as the case with greedy matching. However, it is more difficult to program this algorithm, but there is software that exists and user-developed macros that exist to do this. Another type of matching we can do is matching at both the cluster level as well as the student level. And to explain this, I'll use a sequence of examples. And in the first example, let's think of an intervention that is school-wide in 6 treatment institutions, and you want to find a match of 12 comparison institutions. So you can go out and match on institutional characteristics and find your comparison matches. Once you're done with that, what you want to do is check the baseline equivalence of the individuals between your treatment and comparison groups. If they're equivalent, you're done. You don't need to do anything else. But if they're not equivalent, then what you can do is you can go to the student level and try to do your matching there. So you can identify comparison individuals that are close as possible to your treatment individuals on your demographic variables or your baseline characteristics. In the second example, so that we had the treatment, in the first example, we had the treatment at institution level. Here we have the treatment at the classroom level, but within one institution. Again, within that institution, you can go out and you can find 12 comparison classrooms that are similar. Once you've done that, you check the baseline equivalence of the individuals. Again, if they're equivalent, then you're done. You don't have to do anything. If they're not equivalent, then you do exactly what we just did in the first example, which is try to identify comparison individuals that are similar to your treatment individuals. In the third example, here we have treatment classrooms, but across institutions, not within the same institution. So we can very well find our comparison classes in 2 or more institutions. We don't have to be stuck to one institution like we did in example 2. Again, we go through the same sets of steps that we did before. Check for equivalence. If it's equivalent, you're done. If it's not, then you can select individuals at the student level that are similar. So in example 2 and 3, there were considerations about whether to match within an institution or across institutions. And as you try to decide that, there are going to be some trade-offs that you're going to have to make. So if you match within institutions, you're basically controlling for observed and unobserved institutional level variables. However, there is a possibility, because the treatment and control units are in the same institution, that there might be some spillover effects. And what I mean by that, some of your comparison units might accidentally be exposed to the treatment. And so you want to think about those if you're matching within institutions. However, if you're matching across institutions, you can avoid that spillover effect or that possibility of getting contaminated. It also allows for larger sample sizes. Now, we have matched our individuals. We've used we've identified characteristics, we've used our fancy methods, we've got groups that we think are similar. Are they? We don't know that. We need to check for baseline equivalence. And when we think of baseline equivalence, according to the WWC, we need, and the post-secondary protocols, we think about that, we want to establish baseline equivalence on a pretest measure or probably within the same domain. If those variables are not available, then we want to establish baseline equivalence on a continuously scaled measure of an academic achievement or a measure of SES. And when I say they're similar, what I mean is that they have to be lower than or equal to 0.2 standard deviations. Another thing is your baseline variables have to be included covariates in your impact models. I'm not going to get into a lot more on how to actually do the baseline equivalence, but stay tuned. There's going to be additional technical assistance on this topic. There's also WWC standards brief on baseline equivalence that we will provide those links at the end of the webinar. Another thing that you have to remember to do is that once you've matched, whatever method you've used in matching, you have to account for those methods in your analysis. So, and ideally what we'd want to do is to basically use blocking variables in your model. And so if we think of a block in one-to-one matching, it's basically each pair is a block. If you have 1 to k matching, each of the matched k plus 1 toplet is a block. And in many-to-many, each of the stratum that you've created with similar propensity is a block. Again, not a whole lot of details in this webinar, but we will have, and we do have, resources available that you can take a look at. So one thing I want to point out was the slide I was talking about if you're doing without replacement matching. If you're doing with replacement matching, you still want to hold on to that blocking idea, but what you have to do is create these additional rows or these pseudo rows for each, create duplicate records for each of the use of the control unit, and then make your pseudo pairs or your blocks. But once you do that, you have to remember that we have to adjust the standard errors to account for the replacement sampling that you did. If you've used weights to find your matches, then you have to use your weights in all your analyses, and you have to use survey-sensitive software to get the correct standard errors for weights. You can use, for example, like the SAS survey procedures would be a good way to accomplish this. And then throughout the presentation, I've been alluding to additional resources that we have for you. So here is a peek at those resources. Like I mentioned before, for MAHALANOBIS and EUCLIDEAN distances, it's not built into any core software, but they are good written packages that I've used in the past. An example is this matching package by Dasky-Seacon, and there's a GMAT SAS macro from the SAT department at the Mayo Institute. A very, very helpful link that I always check periodically because Elizabeth Short maintains this online list at a website that's up on your screen right now, and it's very current. Like, she updates it frequently, so I always look at that list whenever I'm attempting to do this. There's also the analysis using propensity score in the reviewer guidance for use with the version 3.0 standards of the WWC guidance, and it's at this link that's on your website for how to account for matching in your analysis methods with an eye towards WWC review. My co-presenter, Chris Price, had a presentation at the PD meeting early in April, and here's a link that you can look at for his presentation again. As well as these are some papers that I always have available and open when I'm doing matching or trying to create my comparison groups for QEDs.